Good morning. Today we're going to talk about section 6.3, applications of normal distributions. Well, recall in 6.2 we talked about probability situations that derived from applications of the standard normal distributions. Well, of course, standard normal means normal with a mean equal to 0 and a standard deviation of 1. Alright, in this section today, applications of normal distributions, I would have probably called this section something else. I would have called it non-standard normal distributions. What do you do in situations where your random variable has a distribution that is not standard? A normal distribution that has a mean either not equal to 0 or a standard deviation not equal to 1. What do we do in cases that are non-standard? Well, recall in 6.2, remember Z is a letter reserved for the standard normal. In other words, the mean is 0. And the standard deviation is, of course, 1. And we made this link up between area under a distribution and probability. If I wanted to investigate the probability that a randomly selected z value is between limits, say, a and b, well, we use the normal Cdf command. Use normal Cdf in your distribution function list on the calculator. You call up this command into your home screen. You plug in a left bound for z and a right bound for z and punch it out, and again your calculator will return the area under the z distribution between these limits of interest, namely a and b. So if I pictorially draw a standard normal curve and I shade in the area under that curve between a and b, this value is really this shaded area which is computed with this calculator function. So remember, there is a link, a profound link between areas and probabilities in these normal distribution applications. Alright, how about where the normal distribution does not have a mean of 0 or a standard deviation not equal to 1? Well, your syntax of the normal Cdf command is something like this. Of course, you call up normal Cdf into your home screen. You plug in a left bound and a right bound and punch this out, and your calculator returns the desired probability. Now this is for the standard normal. Alright, what about the non-standard normal? Well, there are some optional parameters here. If you look in the calculator guidebook, they put them in brackets, and there is an opportunity to put in means and standard deviations in these normal Cdf operators. Right? If you ignore these mu and sigma inputs, the calculator assumes a mean of 0 and a standard deviation of 1. In other words, if you omit these values, the calculator assumes you're in a standard normal situation. Write that down. If omitted, the calculator assumes a standard normal. In other words, the mean is 0 and the standard deviation is 1. Right? But if you do not omit them, if you do plug them in, well, the calculator recognizes as non-standard normal distributions, and you can go ahead and compute the probabilities much like we did in section 6.2. Let's look at an example. Suppose women's heights. We want to consider adult women's heights. I'm going to let the variable x represent all the different heights of all the different women of all time. And I'm going to claim that these women heights are normally distributed with a mean of 63.8 inches and a standard deviation of 2.6 inches. And that sounds about right. 63.8, well, 5 feet is 60 inches, right? So a mean of 5 foot 3.8 inches and a standard deviation of 2.6 inches. That looks good. And with this assumption here, I'll now want to find the probability. That a randomly selected adult woman has a height, well, let's say between 60 inches and 70 inches. Alright, so 60 inches is 5 feet. So what's the probability that a randomly selected woman has a height between 5 feet and 5 feet 10 inches? And you might consider that this probability should be on the high end, right? It seems that most adult women have heights between these limits. Well, we'll see. Alright, so what I really want here is the probability that x, where x is the height of a randomly selected woman, is between 60 and 70 inches. If I were to draw this pictorially, I'll draw a normal distribution that's not standard, right? The mean, as we set up here, is 63.8 inches, so that hump is going to peak at 63.8 inches. And if I draw 60 inches, it'll be left of the mean, somewhere down here, and 70 inches will be somewhere further to the right of the mean there. And remember, the area under the distribution function between your limits of interest is the probability that I seek. So let me shade in this area. This area under the probability density function, the normal curve, is the probability I seek. Alright, we're still going to use the normal Cdf command. Alright, we've got to put in a left limit first, so 60 is our left bound of interest, 70 is our right bound of interest, and because we are in the non-standard case, we've got to plug in a mean of 63.8 inches and a standard deviation of 2.6 inches. Alright, so remember, you get to your normal Cdf command via the distribution button. It's the second level above the vars button. So hit second, vars, distr for distribution, and find that normal CDF function address. Call that function into your home screen, much like we did in section 6.2. And all that's new here really is you've got to plug in your non-standard mean and standard deviation. Alright, if I punch this out, I'll get a 0.92 probability, which really tells me that 92% of all adult women have heights between these limits. Let me write that down. I claim that 92% of all adult women have heights between 60 and 70 inches. Okay? So my answer to this question, as stated, was 0.92. Alright. Let's try another one. Same given information. We're still dealing with women here. I'll say X represents heights of all adult women of all time. I claim that those heights are normally distributed, a bell-shaped distribution, with the same mean and the same standard deviation we used in the last example. Okay? And I'll say find the probability that a randomly selected adult woman has a height greater than 70 inches. So that's 5 feet 10 inches. And you might consider this, well, 5 feet 10 inches, that may be a little tall for a woman. Depends on the woman, I suppose. Alright, I punch this out much in the same way as I did in section 6.2. This is the probability I seek. The probability that x is greater than 70. Again, if I was to draw a picture of the bell-shaped curve, normal curve peaks at the mean of 63.8. Now 70 I'm going to draw up here somewhere. So I want all the area under that non-standard normal curve to the right of 70. Alright, as you might think, this probability is maybe on the small side, greater than 5.10 and all. Well, I'll still grind this out using my normal Cdf command. But remember the syntax. You have to put in a left bound. You've got to put in a right bound here. Now, in theory, this curve goes off to forever, so technically my right bound is infinity, and we've got a little workaround for that, and the mean and the standard deviation we'll fill in a minute. Well, our left bound for our area of interest is clearly 70. My right bound of interest is infinity. Okay. And remember, our author suggests to use 999,999, just short of a million, as our best approximation for infinity. The population mean of women's heights is assumed to be 63.8, and the standard deviation is 2.6 in inches. Alright, so I'll punch this out on my calculator, and I get 0.00855, I'll call it. And rather a low value of probability here, as you might expect. It's something less than 1%, right? Alright, so there's our normal Cdf command with the in the non-standard case. I want to look at another one here. Let's look at example 2. They talk about men's heights in example 2. This is on page 261. Let me turn there myself. I'm going to read the problem just as I see it in the book. You might want to turn there too. The chapter problem stated that British Airways and many other airlines have a requirement that a member of the cabin crew must have a height between 62 and 73 inches. Given that men have normally distributed heights with a mean of 69.5 inches and a standard deviation of 2.4 inches, find the percentage of men who satisfy that height requirement. Alright, so we are told that the heights of adult men, and I'm going to let the variable x represent all the different heights of all the different men of all time. The author claims that those heights are normally distributed. Not too many really tall ones, not too many really short ones. Most are somewhere in a neighborhood of the mean. Alright, normal distribution with a mean of 69.5 inches. Be sure I write this down right. and a standard deviation of 2.4 inches. Alright, we have to find the percentage of men, or the probability really, of that men satisfy the height requirement. Now, the height requirement is between 62 and 73 inches. Let me write this down. Find the percentage or probability of men between the height requirements of 62 inches and 73 inches. Right, what I really want is the probability that a randomly selected man is between these limits, 62 and 73. Right, this is what I seek. And again, I'll draw a distribution, a normal distribution of heights. Again, not too many really tall men, not too many really short men, most somewhere in a neighborhood of the mean of 69.5. And I want the area under this curve between 62 and 73. Now I would guess this was 62 is 5'2", 73 is 6 foot 1 inch, right? So I would expect a large portion of men to be between these limits. Be shaded in. This shaded area is the probability I seek. Alright, again, I'll punch it out with my normal CDF command in this non-standard normal distribution. The left bound is clearly 62, the right bound is 63. The non-standard mean is 69.5 and the standard deviation is 2.4 inches. I'll punch this out in my calculator and I get 0.927, rounding off. This tells me that 92.7% of men satisfy this height requirement. Okay? So I'll say 92.7% of adult men satisfy the British Airways height requirement. Okay, so that's example 2. Alright, what we've done in the last 2 examples, we were given not z-scores but x-scores because we were in non-standard situations, and we found probabilities, and we did that using our normal CDF operator as shown above. Now, just like in the last section, we're going to do this in reverse. We're going to ask, given probabilities, typically in terms of areas under a non-standard normal distribution, we'll work it in reverse and find the x-scores, okay, and the non-standard situation. Alright, let me get a fresh screen here. I want to focus on example 3 in our text on page 263. Well, let me read it to you here. You might want to turn there yourself. When designing an environment, one common criterion is to use a design that accommodates 95% of the population. What aircraft ceiling height will allow 95% of men to stand without bumping their heads? That is, find the 95th percentile of heights of men. Alright, assume that heights of men are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. Alright, so we're talking about men here for this example, men's heights, and I'll let the variable x represent all of men's heights, the author claims that these men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. Alright, now our goal is to find the 95th percentile. Let me draw a little picture here. These heights are normally distributed. Not too many tall ones, not too many short ones, most somewhere in between. I'll draw the peak of the bell at 69.5 inches. Alright, my goal is to find the height that separates the bottom 95% from the top 5%. I'm going to draw it right here. Right, this is the x score that I want, the x value that I want, such that the area to the left of that value is 0.95 and the area to the right of that value under the distribution curve is then 0.05. Alright, much like we did it in section 6.2, we're going to use the inverse norm command. And you might guess that the inverse norm command, well, remember, the way the calculator has got it set up, you have to input your left area. But again, the inputs of mu and sigma, or for mean and standard deviation, are optional. If you leave them out, the calculator assumes a standard normal. Well, here we are not in a standard normal, so I'm going to input those optional values. The area to the left of this designated value is 0.95, as seen in the picture above. The mean, I'm going to enter in a 69.5, comma, and the standard deviation is 2.4. Alright, so again, we'll grind out this score with the inverse normal command. I punch it out, and I get 73.4 in inches. Alright, so let me check things out with our picture. Yeah, that looks about right. So you might guess that this value is going to be significantly to the right of this value, and it appears that it is. 73.4, that's 6 feet 1.4 inches. Right, so all men that height or under will be able to stand in this cabin without hitting their heads. I think that's the idea. Okay. I want to look at example 4 in the text on page 264. And again, I'll read it here. Alright, they talk about ability grouping and with regard to IQ scores. Some educators argue that all students are served better if they are separated into groups according to their abilities. Assume that students are to be separated into a group with IQ scores in the bottom 30%, a second group with IQ scores in the middle 40%, and a third group with IQ scores in the top 30%. Alright, the Wessler IQ scale yields an IQ score obtained through a test, and the scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the IQ scores that separate the three groups: the bottom 30%, the middle 40%, and the top 30%. Well, the first thing I'm going to write down is that IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So 5 there. Okay. Alright. I want the scores, the IQ scores that separate the bottom 30%, the middle 40%, and the top 30%, right? So here's my distribution of IQ scores. It's normal, which means it's bell-shaped. The bell peaks at an IQ score of 100. Alright, I'm going to draw a score here. I'm going to label it X, and I'm going to say that score will cut off the bottom 30%. In other words, the probability being less than that value is 0.3. Alright, I'm going to draw another X score that's going to separate the middle 40%. I'll put that with a green X. Alright, so there is the middle 40% of all scores indicated by that area in between. And then the probability of being above this value, well, of course, the total area under the distribution is 1. So that means this blue area is going to be 0.3, or represent 30% of our distribution. Alright, so I want to find these scores, and I'm going to do it using the inverse normal command. To find this X value, I'll use inverse norm, and remember the syntax. You got to plug in the area to the left, and the mean. The mean is floated up screen. The mean is 100, and the standard deviation is 15. Okay, this is the X value I seek, and if I punch this out on my calculator, I get a 92.13. That looks reasonable. The mean is 100, so certainly X, this pink X, is going to be significantly less than the mean, 92.13, and that looks good. How about this green value here? Well, in the same way, or similar way, I suppose, I'm going to use the inverse normal command. Plug in the area to the left. Now, area to the left means total area to the left. And I think you can see that's going to be an area of 0.7. And again, the non-standard mean and standard deviation. And if I punch this out, I'll get a 107.9, we'll call it. Alright, so these two scores separate the bottom 30%, the middle 40%, and the top 30% of all IQ scores. Alright, so much like we did in section 6.2 with the new wrinkle, and really the calculator takes out a lot of the drudgery that we ordinarily would have used tables and other formulas to compute these values. Alright, we'll call it a day, and this concludes section 6.3, applications of normal distributions.